of course, the cuprate superconductors date from 87. That's what, how many years ago is that? That's like 30 odd years ago. And if I work it out right, it's about 21 years between discoveries. So we've got another 7 years to go before the next big high TC discovery. Anyway, in the meantime, this is the endearing mystery, and welcome back, Amalia.
Thank you very much for having me. Thank you for being here this afternoon, and thank you, please, for the invitation to be at this interesting meeting. So in my talk today, I will provide a bit of a summary of what happened over the last few years in trying to understand electronic behavior of a family of iron-chalcogenide superconductors. Just a few remarks to thank people involved, members of my group, current and former members. We've done lots of experiments at the diamond light source, at IO5. Samples were prepared by Amalia, both in Oxford and Germany, and we've done experiments also various facilities in the world, in USA, in Nijmegen and Toulouse. So in my talk today, I'm going just to focus on a few aspects which are covered in this different type of publications. In particular, from our experiments, we try to identify what are the signature of nematic electronic phases. Then from quantum oscillations, we were looking to understand how if there is a nematic critical point, and how does it behave from in terms of what happens to the quasiparticle and if they are divergent behavior. And then we then also looked at transport and magnetotransport in these nematic phases to try to identify their signatures. Obviously, the systems that we are dealing with are multi-band systems, which makes sometimes obviously understanding their behavior much more complicated. So here is a three-dimensional phase diagram of the family of iron selenium. So iron selenium is supposed to be one of the simplest material binary system. So if we understand a simple system, hopefully we can move forward in understanding of complex unconventional superconductivity. And this material is special for many reasons, but in the bulk form, so these are single crystals grown with a chemical vapor transport. It has a nematic electronic phase, which is quite unique in the fact that often there is a magnetic phase following up a nematic phase in iron superconductor, but this nematic phase in iron selenium, it's robust, a very low temperature just before the superconductivity sets in. So that means we are able to understand better these nematic phases using different tuning parameters. So what we have here, we have sulfur substitution. So we have selenium and sulfur are above the conducting ion planes. So we replace isoelectronically with selenium, selenium with sulfur or tellurium without doping the system and without really altering too much what happens in the conducting plane. But when we do this type of doping, so sulfur is here, nematic phase is suppressed, the superconductivity is the pink region. We see that superconductivity is kind of becomes smaller when right when the nematic phase is suppressed. Then eventually the system enters into a double strike magnetic order. And under pressure, it's even more remarkable that superconductivity is enhanced a factor of 4. And that occurs when signature of spinless QA phases are nearby. Besides, obviously, understanding the interplay between nematicity, superconductivity, these materials also have other interesting new signatures. For example, topological superconductivity has been proposed to exist at about 50-50 substitution of selenium and tellurium somewhere on the top of the dome here. So that would be a topological superconductivity when you have surface topological states, but the bulk still being a normal superconductor. So this ideal setting for a system. And another proposition made recently is that these materials could also harbor unusual time reversal symmetry and potentially there could be a system where we could look for Bogoliubov Fermi surfaces in the tetragonal phases. So another reason why we would like to understand the system, obviously, is that it has a very large TC in a monolayer form. So this is the record holder for a 2D superconducting system, which reaches about 75 Kelvin. And this is a phase diagram of TC versus electron doping. So how does electron doping occurs? You can take a ball crystal and you evaporate potassium ions, or you introduce via gating electrons into the system, and you can enhance superconductivity from about 10 Kelvin to about 40. And then in monolayer systems where you have strontium titanate substrate, you grow one single layer of iron selenium, then this is where TC is very enhanced. And those type of Fermi surfaces, which seem to hold this high TC, are those only having electron-like Fermi surfaces. So it's clearly that the doping is very important to boost the superconductivity. But today I'm going to focus mainly on the low TC aspects and how those signature and the interplay with nematicity may be important for superconductivity itself.
Amalia, can I ask a question on the phase diagram from the previous slide? So the spin density wave is again this pi zero ordering vector, or?
Well, there are no neutron diffraction, but it's believed to be collinear antiferromagnetism. Indeed, that's a proposal. However, there are no direct evidence from neutron diffraction because experiments are not.
But here, I mean, it seems that the nematic is decoupled from this magnetism, but still, for general grounds, one would expect that there is a precursor nematic transition. Again, it could be unrelated to the nematicity in this zero pressure region, right? But
that's right.
Can you rule out that there is maybe a 1 Kelvin region, nematic region above the SDW as well? Or?
So I think, well, I'm not going to talk too much about this phase because actually this is some research we're doing right now. From the phase diagram itself, what's interesting is you see that both the superconducting and the SDW seems to follow each other initially, which is a bit unusual. So some USR data predicted that you might have coexistence between the two phases, at least in this regime. Okay, so let's just here, I summarize a few aspects about the characteristics of these materials and how we can think about their important elements. So as I said, we have multi-bands. So we have hole-like pockets at the center of the brilliant zone. The different colors illustrate the changes in the orbital characters. So we have XZ and YZ orbital characters. Those are degenerate in tetragonal phase. And then we also have the XY orbital character, which appear on the electron pockets at the corner of the brilliant zone. The systems are strongly correlated, and also the way the magnetics behave is very important and not easy to understand because we are dealing with itinerant systems. So this magnetic moments are likely to fluctuate a lot. And probably that's also the reason why iron selenium never orders. There's been suggestion that it could be a competition between different type of magnetic order, which are trying to destabilize, but eventually, even if it doesn't order, we should assume that those magnetic spins are still there, and some of them are likely to be important for scattering. And another thing, when we extract various parameters about these materials, often the dxy orbital character of these bands is also more correlated. So we have this differentiation in correlation depending on the orbital characters of the bands. Now, when we think about the nematic phase, which occurs to a particular transition, we have to consider the different types of scenarios which could rise to those phases. Well, first of all, we have a breaking in, so the symmetry is changing from C4 to C2 symmetry as the system goes through a transition, which also has structural changes from tetragonal to orthorhombic. At the same time, because we have the dxz and yz orbital degenerate in tetragonal phase, we expect that the lifting of that degeneracy is the trigger to cause orbital and charge ordering type effects and gives rise to kind of a changes in the population of the bands with xz and yz character, leading to their distortions in different ways depending on how they are of their orbital character. Obviously, nematic effects could also occur due to the anisotropy in magnetic systems, so susceptibility along different directions to become very anisotropic as the system cools down. Now, the reason why the nematic electronic phase are believed to be the leading proposal for the transition we observe is because if one tries to measure the resistivity itself along the A and B directions, as the system will enter this nematic electronic phases, the anisotropy is really, really large. So here we have a factor of about 8 or more, whereas the changes in the lattice parameters are very tiny. So that means that the lattice itself is not producing enough changes to explain the development of this strong anisotropy. Obviously, a proposal made in 1959 by Pomeranchuk already told us that if a system is a Fermi liquid in the presence of strong interaction, also can spontaneously distort its Fermi surface and gives rise to this nematic electronic phase. Now, in terms of the spin density wave, we have electron and hole pockets, and in many iron-based superconductor, the spin fluctuation has been proposed as the mechanism for pairing. And that's because here the hole and electron could nest. We have a large density of states, and that could enhance the Wien-Hart susceptibility. And usually in the phase diagram of many iron-based superconductors, you have a spin density wave. The parent compound often will order magnetically, and then if you dope with electron and hole, a superconductivity appears. So that's the standard proposal that iron-based superconductor are the prototypical system to look for spin for superconductivity driven by spin fluctuations. And the type of pairing expected is S plus minus, meaning the gap will be positive on one side and negative on hole pockets and negative on the electron pockets. So there is the wave vectors that connects hole and electron pockets will also enable the pairing, and it has to be S plus minus because this type of interaction will be not attractive. Okay, so firstly, I will just show you some of the phase diagrams by varying other parameters in iron selenium. Here is actually, before that, how is the behavior of the system as a function of temperature? So its resistivity, first of all, we have quite a bad metal at room temperature. It goes through this transition, a TS, and then it's almost linear resistivity before it enters the superconducting phase. In the tetragonal phase, the standard method to establish that the system has nematic behavior is being measurements of its nematic susceptibility. So what that means, we take a material, we place it on a piezo stack, we apply a small amount of strain to it along the direction which will break the symmetry, And we measure the elastoresistivity response, in particular the M66 parameter, and that represents the nematic susceptibility of the system, and it has Curie-Weiss-like behavior. So this is equivalent to what often we search for a magnetic system when we measure magnetic susceptibility. In nematic system, we measure their nematic susceptibility via a small amount of strain. And another signature, obviously, the system indeed will have the transition from tetragonal to orthorhombic and a small distortion of its lattice as well. So I will focus on the ARPES data in these two family of compounds as we suppress nematicity both with sulfur and selenium. And already we can see here that there are some asymmetry between the two sides. Here the system eventually becomes more localized, and here is much more metallic and correlations are weaker. With pressure, clearly there are some other important ingredients are important. So we see initially both applying pressure to the system reduces its volume unicell. We've suppressed superconductivity. There's a tiny little dome of superconductivity there. And the same thing happens when you use chemical substitution. And this is because sulfur is smaller than selenium, so in a way it has an equivalent effect like applying pressure to the system. But afterwards, after this nematic phase is suppressed, the two systems are not equivalent anymore. That means there are some additional ingredients occurring under pressure. And having this isoelectronic substitution, one can play with different concentration and apply pressure to them. And it's quite beautiful to see that in iron selenium, the spin density wave is more or less merging inside the nematic phase. But as we add more and more sulfur, we can push those states apart. So this gives us access to each phase individually. And I'm going to show a bit of data from the 11% sample where we were looking to explore the nematic critical regime. Now, what happens if we add an impurity to the system? So interestingly, if we add a copper impurity in this conductive layer, then the material becomes very non-metallic. And one can look at the variation of TC versus the residual resistivity and establish that this follows the Ablytosov-Gorkov formula for an S plus minus system. So this is equivalent to what has been done in cuprates in the case of a magnetic impurity. So when we have a sign changing order parameter, then we need a non-magnetic impurity to follow a similar formula. So TC follows this. That means we are likely dealing with an S plus minus superconductor in iron selenium. And also the nematic phases and superconductive phases seems to be affected in a similar way by impurities. Another thing one can, yes?
Surely that just means you've got a change of sign in the order parameter somewhere. It doesn't have to be S plus minus.
That's right, yes.
So also you would expect that there is some mixture of something else, right? Because it's born out of the nematic state.
Yes, yes. So indeed, the iron selenium is in the nematic phase, and this is where we alter that phase. So inside the nematic phase, you need to have pairing, which I'm just going to mention, are likely still to be the spin fluctuations. Iron selenium is also great because you can exfoliate the system. You have van der Waals layers. And here we created devices by flaking our crystals in thinner and thinner layers. And in the similar way, like we saw with the copper substitution, actually both the nematic phase and the superconducting phases were suppressed, which is different from when you grow the material in a monolayer. But if you apply strain to the material, so now here we have iron selenium under strain, we use the razor bill type of cells. We glue our crystals between two plates and then strain it. and focus here on the superconducting regime, well, we found that the superconductivity is enhanced with compressive strain. And this is equivalent to what happens if you grow this material in thin films on different substrates. But this time, the superconductivity and the nematic effects do not seem to follow each other. So that means the effect of the strain alters somehow the relationship between the two phases. Okay, so now I'm going to talk about the electronic structure inside this, the nematic electronic phases. So here it's an output spectra of whole bands, the tetragonal phase. It shows two different crossings, and this is the band structure calculation on the right. So already we see that instead of having 3 whole bands crossing the Fermi level, iron selenium only has 2 of them at the Z point. And here is a direct comparison between DFT. So these are 3-dimensional Fermi surfaces with 5 different bands. And in the tetragonal phase, we are only left with 4, and one of them is only visible. It's only it's left at the Z point. So you have like a 3-dimensional little pocket at the Z point. And
quick question.
Yeah.
Not only did that gamma band not seem to cross the Fermi level, but it didn't seem to be there at all.
I'll show you in a minute. These are very high temperature data. So when we go to low temperature, we start seeing that band from the hybridization. So at high temperature, things are getting fuzzier, and when there are weak effects, you can't see them, unfortunately. So when you compare RPES and DFT, then you can look at the different band renormalization. And as I mentioned before, in iron-chalcogenide in particular, if you look at the XZ and YZ band, they have a factor of about 3 to 4. Whereas if you look at the DXY band, which I'll show you in a minute, this renormalization factor is 8 to 9. So we have this very unusual orbitally dependent renormalization effects. We also measure quantum oscillations. So these are resistivity versus magnetic field at very low temperature. We show the oscillatory signal. This signal is Fourier transform. And then all our data as a function of our angular plotting in this color plot. So what is this telling us? If we have a cylindrical Fermi surface and we plot f cos theta, we have a branch which moves like this. If it's a minimum, it should move slightly up, and the rest of the branches should come from other pockets. These are on the left and right are the Kaiser dependence RPES data showing that our pockets are quasi 3-dimensional, and we are likely to have a hole and an electron and potentially another small electron pocket in iron selenium at low temperatures. Now, why this shrinking occurs? So this is quite unusual. We discussed about the correlations are very important, and how the shrinking occurs is very unusual in the fact that both the electrons and holes are shrunk together. So here are the data from quantum oscillations, and these are the predictions from DFT. We have a factor of about 5 smaller pockets than what the calculation predicts. These are some theoretical calculations of including the nearest neighbor interaction in the presence of spin-off decoupling, and those type of interaction indeed can lead to shrinking of the Fermi surfaces. Another important thing we have here, because of the nesting effects, those type of nesting interactions, so the intraband interaction between hole and electron pockets can also lead to this severe shrinking of Fermi surfaces. Iron selenium also shows some signature of the lower Haber band, so that it's the signature that it's a strongly correlated system, and these are DFT calculation performed by José Valenti's group. And even if this type of interaction are taken into account, these are the calculation here, and these are the experiments on the left side, the Fermi surfaces are still not fully captured at very low energies. So when when we go through a nematic transition, the system potentially could also form twins. And in order to avoid this, one has to apply a small amount of strain, which was done in this experiment, to be able to see what is the precise Fermi surface. And by detwining the sample, was established that the hole pockets elongate along one direction and the electron pockets along the other direction. So we have a momentum-dependent change in the way the Fermi surface elongate as a function of applied strain. And the STM data have also shown that that these pockets indeed can explain the behavior of the superconducting gap, which is extremely anisotropic, and also changes sign on the hole pockets of electron pockets. And this requires the spin fluctuation and orbitally dependent correlation to be active to explain the existing data. So these are neutron diffraction data performed on single crystals. We show that the peak in the imaginary part of spin susceptibility is enhanced when the system enters the superconducting phase as a signature for mediation, spin fluctuation mediated superconductivity. To understand the upper critical field, here are some of our recent data. We can use the multiband description, having hole and electron pockets, and to try to fit the upper critical behavior, which is almost linearly dependent on temperature along when the magnetic field is along the z-axis, and it has a slightly different behavior when the field is in the plane. So here our parameters used to model this behavior also requires that the interband interactions are much stronger than the intraband interactions. Again, supporting that S plus minus is likely a good contender for this behavior. Yeah. So we play with various parameters for the, so we included some parameters intraband interaction. So lambda 1 is kind of the interaction for the one pocket. And if it's finite, I think pure will mean that these parameters would be 0. So it's mainly dominated by the interband interaction. It was just how the students was playing with the parameters to see which one would be the best. That's right. I mean, I think I would encourage this type of calculations to be done starting from the band structure and really accounting for everything. What we took from literature an existing model by Gernevich, which I think it's developed for multi-band, probably 3-dimensional Fermi surface. And we just try to understand which parameters will be suitable to describe both orientation with the same type of parameters. And obviously, this gives you information about the Fermi velocity anisotropies. Yes, but in reality, if we want to be very precise, it would be great to have the precise Fermi surface included in the model.
Did you include the on-site Coulomb interaction in this calculation?
Here,
X plus minus is, unlike D wave, is very delicate. It doesn't have a symmetry protected protection against on-site Coulomb.
So, as I said, this model was developed for multi-band system. I can't tell you all the details what was included there, but I think it was even developed for MGB2. So I assume it's a more conventional superconductor, and the effects are not included. So now let's look at what are the effects expected when a system goes into a nematic phase. And this is a paper by Fernandez and Oscar Bachek, giving us guidance of where we should look for the nematic signature. And the first one is if we look at the hole pockets at the gamma point, the splitting between the different hole bands should contain both a nematic term and also spin orbit effects. And actually, it will be given by this expression. Whereas if we look at the electron pockets, then there the lifting of the degeneracy in this symmetry will be affected by both the nematic effects due to the xz and yz, because we lift that degeneracy, but also because we develop anisotropy in the Hoping terms of the dxy orbitals. And in there, this type of effects will be much more complex. And we should expect, so by symmetry, so we have two electron pockets here, and they should be degenerate in the tetragonal phase. And actually that degeneracy will be robust even against the spin-orbit coupling. It's only when we introduce the nematic effects, we should see those changing. And this is just some simulation of how the Fermi surface should evolve. When you turn on the nematic effects, obviously you will start distort the Fermi surface and also shift the bands. So whole bands, top band in relation to the bottom band, because this is where the nematic order parameter could be detected. And for the electron pockets, things will be much more complicated, but eventually we should expect to elongate these pockets. In reality, things are much more complex than this little cartoon. So here are some data how the Fermi surfaces of a nematic system will look like. This is a twin crystals. So you have to imagine the superposition of two nematic domains rotated by 90 degrees. We saw earlier that when we apply strain, we only see one particular one. And when we change the sulfur concentration, the system becomes more and more isotropic. And obviously here it fulfills the 4-4 rotation symmetry as expected from calculations. The electron pockets usually have this two ellipse, cross ellipse, and the spacing between these two cross ellipses should be lifted by spin-orbit coupling such that we have an inner and an outer hole pocket. And inside the nematic phase, they do become extremely elongated into peanuts-like shapes. And these are the dispersions. Obviously, when we measure the different bands, if we look carefully, there isn't too much change. What really happens is that this inner hole band, which is shifted below the Fermi level, so it's just about shifted below the Fermi level at low temperature, it's starting to cut back, to go up as we add solvent. So there are very subtle changes in that inner hole band. And here we can see the dxy band from the hybridization with the other band. So this is where it lives. It is about 50 electron volts below the Fermi level. If we look at the whole, the gamma point, similarly, we can see the dxy band, how it changes with the substitution, and we only have a crossing here. But the most striking effect is the electron pockets here. We are supposed to have two parabolic dispersions, and what happens is that a weak parabolic dispersion is often seen. The second one is weaker in intensity, but then below the Fermi level, there is a very unusual splitting and changing in the intensity of the spectral wave, as if we develop some sort of gap below the Fermi level. If the tetragonal Fermi surface of these materials actually surprisingly is very similar to what we see in iron selenium in the tetragonal phase. So that's why this electronic substitution is quite beautiful, because we can recover that tetragonal phase we started with a high temperature. And sulfur substitution is a very, very clean tuning parameter. So when we look at the data, I just show you that in our experiments, when we measure the spectrum, we have to be aware that different light polarization affects the intensity of the different bands. And this is because we have the dxy bands, the dxz bands, and the way the intensity changes is because of the matrix element between the light polarization and the orbital character of the bands. Now, this type of Fermi surface in the tetragonal phase has been suggested to harbor this Bogoliubov quasiparticles, Bogoliubov Fermi surfaces. And this, I just wanted to show here what has been recently reported using laser ARPAs. That means when you measure with laser ARPAs, you have very high resolution. However, you can only probe a very low momentum space, and often is at the gamma point. So here are laser ARPAs on a tetragonal iron selenium sulfur, in which is being claimed that there is a strong anisotropy of the gap and the formation of this Bogoliubov Fermi surfaces inside the superconducting phase. And these are our tetragonal Fermi surfaces showing the whole Fermi surface, which in my view bears the same signatures like in the tetragonal phase of iron selenium. If this effects also occur on the other bands, or how exactly this might manifest for other pockets, remains to be understood. Yeah. I think, well, these spectrums are taken using different light polarization. As I mentioned in here, using different, this is LV, linear vertical, linear horizontal polarization, you see different bands, different dispersions. And here is the same. Using S and P polarization is equivalent to that. That means when you see here, you are mainly sensitive to this pocket, very likely because of a particular orbital character, whereas in the other polarization, you are sensitive to the other pocket. But then they measure the gap of these pockets, and they suggest that there is a very anisotropic gap in a system which is tetragonal.
Sorry,
yeah.
Just to check that I'm understanding the picture, is the idea then that there are whole regions of the Fermi surface on which the superconducting gap is zero, but they're not Fermi arcs, they're actually reconstructed into pockets?
Yeah, I think this will be a Fermi surface in the superconducting phase, what they are claiming. So there is a density of state, a finite density of state originating from this type of entities which form there.
Is there any other evidence for broken time reversal symmetry?
So there are some MUSR data suggesting that that could be possible, but time reversal symmetry has been suggested to occur everywhere, not only in the tetragonal phase, but also where the nematic phase is. So, I mean, this proposal has been for tetragonal case, so I don't know how that is reconciled with this. Because if time reversal symmetry is everywhere, then we should see these effects in other places, I suppose.
If I look at the original proposals, theoretical proposals, you need quite a lot of spin-orbit coupling.
So we do have about 20 milli-electron volts is the spin-orbit coupling in the system. So it's quite sizable. Okay, well, this is just a summary of the data we got to characterize these nematic phases. Obviously, the most obvious behavior is that the pockets distort, and we can quantify this degree of distortion. Both these are for the hole pockets, and these are for the electron pockets. The energy scales are quite small, but still up to about 20 milli-electron volts. And the superconducting gap determined by STM by Hanaburi group, it's up to about 2 milli-electron volts. I mean, this type of the ratio between having low Fermi energies and superconducting gap has been also proposed that in some systems, there may be conditions for the BCS-BAC crossover. And here, now I'm showing you some new data about what we try to measure in the nematic phase when we use tellurium. So the same like previously for the selenium case, we have the band dispersion starting from iron selenium and the BXY band. We observe some changes in the relative intensity between the inner and the hole pockets. And when we look at the second derivative, which emphasizes the observed crossings, what is interesting is that this dxy band, which was living happily below 50 electron volts in sulfur series, now is shifting up and is coming towards the Fermi level. And if we put all this data together and actually we model using the 3-band model our dispersions, we can extract the information about the shifting of this dxy band and the effective masses associated to it. And interestingly, in the tellurium series, nematicity is suppressed, but then superconductivity shoots up again. And if we look at the correlation between the presence of the second superconducting gap, we notice that the dxy band is coming towards the Fermi level more or less when this gap starts to, when this superconducting dome starts to increase. So it's likely that we have a new pairing channel now given by the dxy band, which potentially helps to boost the second superconducting dome in iron, selenium, tellurium. Well, at the same time, the effective masses associated with this very correlated band seems to increase significantly as well. So it remains to understand how a correlated pocket or a pocket which can give a lot of density of states helps to boost the superconductivity about the factor where it's about from about 5 to about 12, 13 Kelvin. So quite, factor 3. So yeah, these are the new results we have. It's worth mentioning these materials at the 50-50% concentrations are the materials proposed to host topological superconductivity. If we are looking at the DFT as a guide, which usually provides the guide about the trends of the system, but does not provide the exact value because the Fermi surfaces are shrinking. So when we calculate the changes of the dxy band, so this is the blue band here, by changing the chalcogenide. So as you add tellurium, you move the tellurium away from the conducting plane. So that's given by this chalcogenide. And the calculation predicts that this band should move up. And here we plot how this shift occurs. And in the end, DFT gives us a guidance that this band indeed will shift as we add more and more tellurium. On the second row here is what happens to the chalcogen PZ band. This is the one which is important for topological effects because it will cross with the other bands at the Fermi levels. So this purple band here, as we added more and more tellurium, eventually comes across at the Fermi level, and these are the conditions in which you start having the surface states, which are Dirac dispersion due to the crossing with this purple band.
You have similar effects with C-axis compression, or would this not be strong enough?
So this is C-axis compression occurs when you put sulfur. Here we have expansion. So C-axis gets larger when we add tellurium. So it's the opposite effect to that. So to bring the PZ band down to the Fermi level to create this topological potential crossings, we need to bring to increase the size, to separate the ion layer from the pictogen.
And it's possible to bring up the other band and suppress the XY you had originally at the demo point? Or?
I mean, as you see experimentally, it's the first time we see the DXY band nicely shifting away. We always thought that it was quite immune, but it seems like it's very sensitive to tellurium substitution. So I think now we have a cocktail of lots of bands, low energy interactions, and a PZ band happening as you are on top of the dome. So I think it's quite a rich environment for for physics at that particular point. For the electron bands, things are a bit more complicated. As I said, we should have 2 electron dispersions, and then if you go inside of an orthorhombic phase, one should split the various crossings here, which were degenerate in the tetragonal phase. And these are the signature that one can see in experiments. It's very unusual splitting between the 2 features in the RF spectrum. But the final splittings also exist in a tetragonal phase. So if you put all this information on the phase diagram, we see that this kind of quasi-splitting, which occurs for the electron pockets, it's strongly linked to the transition temperature of the system. So obviously, it has a strong link with nematicity and potentially with the lattice effects as well. Okay, how much time do I have?
Well, you started quarter to past, I think, so lost. 25 minutes.
Okay, so now moving to transport and magnetotransport behavior inside the nematic phases. So again, the phase diagram of the iron selenium sulfur, we go from the nematic, we have a little dome inside, and then we go into the next region in the tetragonal phase, which has been postulated that it could harbor a different kind of superconductivity. These are the resistivity curves. We can see that they are quite nicely evolving from kind of bad metal-like behavior to eventually a Fermi liquid behavior for the N compounds in iron sulfur. If we look at the tellurium end, as I mentioned before, the system is somehow different in how the electronic behavior is, but also in resistivity. So these are shifted curves, but at the bottom is adding more and more tellurium. And you can see now the resistivities are almost flat, and then suddenly when superconductivity occurs. Probably this is a better representation of the ratio between high temperature and low temperature, which tells you if a number is small, close to 1, the system highly changes with temperature. So it's a very bad metal. So we have, on the tellurium side, the systems are quite bad metal, and resistivity highly changes with temperature before a system becomes superconducting. But on the sulfur side, we have very good metal, and we can see beautiful quantum oscillations. And these are some of the data in magnetic fields as we change the substitution. So this is the 4% substitution, 12%. And as we increase substitution, what we notice that this oscillatory spectrum, which is complex because we have multi-band system, it seems to become dominated by a low frequency. And we can start seeing that this low frequency gets stronger and stronger, and eventually it disappears together with nematic phase. So why this low frequency could occur? I mean, RPES told us that there is a small 3-dimensional pocket which will show up as we add sulfur substitution. So one potential reason is because of this particular pocket. Being a smaller pocket with larger mobility, it could dominate the resistivity in a multi-band model, assuming that this behaves like a parallel metal resistor. But if we also now check the magnetotransport behavior of these compounds, so these are measurements, rho xTex, so longitudinal resistivity in magnetic fields to about 33 Tesla. As a function of different concentration, we also notice some peculiar features in different regimes. So for low concentrations, where this pocket, we only have one whole pocket now crossing the Fermi level, what we notice that the resistivity in high magnetic fields, this is already a factor 2 larger than the upper critical field, still has the signatures of as if it has some strong fluctuations, potential superconducting fluctuations. So it has a peak and then it drops down. So this system should be in the normal state by now. You know, we are measuring here in 34 Tesla. Upper critical field of this material is about 16 Tesla. So it's a factor 2 higher than upper critical field, and it has the signature in this regime. So all the resistivity dropped down below the expected superconducting transition. So surely this tells us something that we still don't understand. Now, when we go to higher concentration, when we are bringing the inner hole band, crossing the Fermi level, now there is an opposite effect. The resistivity have a strong upturn up, as if there is another anomaly happening there. So you see, as we go in the space diagram, the transport and the magnetotransport really changes quite sensitively where we are in the phase diagram. And if we put all these results together, what we observe is that in general, the Fermi surface do increase with chemical pressure, but there is that particular low frequency, which we call lambda here, which seems to appear at the same place where the slope of resistivity changes. So here we plot, you see this is a different slope than this slope. And here we have the color represent the changes in the slope inside the nematic phase, and we call it nematic A and nematic B, just to emphasize that there are differences in the magnetotransport behavior already inside the nematic phase. So there are two signatures in the B phase, let's call it. It's a dominant low frequency appears, and the resistivity at low temperature shoots up. As if the system becomes more localized or orderly magnetic, we don't know exactly why. And this low frequency, which appears, seems to disappear together with the nematic phase. So it's clearly linked to what happens there. Here I show some more data using the pressure. So we did a similar experiment now with a single compound, but changing the pressure across the nematic endpoint. And similarly, as we approach here the nematic endpoint in this green region, the magnetoresistance is extremely large and dominated by this low frequency. So this data are always reproducible. We always pick this up in the vicinity of the nematic phase transition. And also the amplitude of the high frequency quantum oscillation, it's sensitive to what happens. Its amplitude is very much suppressed. You see, it should be somewhere here, but it's very much suppressed. So there are likely to be other type of scattering processes occurring there, which to explain all this behavior. What else could happen? Obviously, we could have spin fluctuations. If we measure resistivity with a magnetic field applied along the AB plane, such that which we suppress the magnetoresistant effects, what we see that if a system is slightly more disordered, it seems to have a pretty linear resistivity all the way to low temperature. If the system is very clean, it has a linear resistivity, very close, to zero, but then it enters the Fermi liquid phase. And here we plot the phase diagram of this linear T resistivity behavior inside the nematic phase before the system enters the Fermi liquid all the way at low temperatures. And this seems to correlate with the presence of spin fluctuations, which have been detected by NMR data. So potentially inside the nematic phase, we have quite strong spin fluctuations, which are affecting the transport and the scattering in this regime. Hall effect is a Hall coefficient. It's been used a lot in cuprates to justify changes in Fermi surface reconstruction and other effects. Now, in a multiband system, if the system is very well compensated, we should expect that the Hall coefficient should be zero. So a high temperature, indeed, we find that the Hall coefficient is zero. Now, when we reach the nematic phase for iron selenium, suddenly the Hall coefficient becomes strongly negative. And it's as if the system enters, loses carriers. But obviously, we already seen that the Fermi surface is only distorted. So how is possible the system to lose its carrier? So a potential explanation is actually that there are some scattering processes which are very strong in certain direction, as if those electrons which are involved in those processes do not contribute to conduction anymore. So we have like a short circuiting of the system, and we only see the kind of the most conducting channels, whereas others are not visible because of scattering. Here we've done a similar experiments now in thin flakes. So here again, it's Hall coefficient versus temperature for a thin flake of iron selenium. This is the bulk effect. And when we make the system, well, it's only 125 nanometer, but the Hall coefficient becomes quite sensitive to this change in thickness. If we extract the carrier numbers from here, assuming a 2-band model, you see the N values seem to change, to drop, and then recover a low temperature. And if we look at the mobilities of this such a system, the Hall-like carriers remain quite robust for no matter how we change the thickness. So, I mean, it gets smaller a bit as we make it thinner. But what's unusual is the electron pockets are very much sensitive to what happens when we reduce the thickness of the thin flakes. As if those electron pockets at the corner of the brilliant zone become somehow more localized, which probably again is telling us that there is a lot of scattering between them. One more unusual effect of this anisotropy also occurs in the quantum oscillation if we measure the rho xx component versus rho xy. So if you do a Fourier transform, we see that the rho xy Fourier transform has 3 different features. So these are measurements up to about 90 Tesla, so very high magnetic fields. But if we measure the rho xy component and do its Fourier transform of the quantum oscillation spectra, we are missing one of the pockets. And so how we try to explain here, it was that if the system has very mobile Hall carriers, like we saw before in thin flakes as well, then that signal will dominate the rho x component much more than the rho xy. The highly mobile carriers will dominate the rho xy more than the rho xx. So these are the ratio in amplitude caused by the Hall pocket or the electron pockets. And if one plugs into a multiband model, can try to explain the differences in amplitude in quantum oscillations. So the rho xx and rho xy component seems to be affected in a different way. And this is a possible explanation proposed by, in this paper, is that when we have strongly dependent, momentum-dependent spin fluctuation and strongly elongated Fermi surfaces, then we might expect strong anisotropy in the lifetime of excitation in the Fermi surface. And here they model the behavior of the Hall coefficient as a function of temperature as one increases the elasticity. So more elongated the pockets become, the stronger the effect in the Hall coefficient is. Okay, and in the last part, how many minutes I have left?
About 50 minutes or so.
Okay, so now I'm going to talk a little bit about the nematic endpoint where we've been searching for evidence for critical behavior. So in a nematic system, has been proposed for a while now that it is a potential location to find very strong fluctuation of the nematic phase transitions and for the superconductivity to be strongly enhanced. We should be expecting then divergent fluctuations, and enhancement in the effective mass as we approach such a point. Obviously, in those particular regime of strong critical fluctuation, we might have non-Fermi lipid behavior and a large resistivity. So the existence of the nematic critical point has been postulated also to occur in iron selenium sulfur based on this nematic susceptibility data. So as I mentioned at the beginning, this type of technique is used to probe the presence of the nematic electronic phase, in which we look at the development of anisotropy in the presence of a very small amount of strain. And the Curie-Weiss-like behavior is used then to plot the intercept, so kind of the Curie-Weiss temperature. And when the Curie-Weiss temperature, so this is T theta, will go through 0, this has been suggested that that's the nematic critical point. So here it's very close to the phase transition between the nematic and the tetragonal phase. Obviously, these are based on assuming a Curie-Weiss law, which usually normally is a mean-free type behavior. And to really probe the existence of critical behavior, we need to look at the behavior of the quasiparticles at very low temperatures. And to do that, we need one method is the quantum oscillations, and looking at the effective masses detected from these experiments. We measure these are amplitude of the quantum oscillations for different temperature. We look how the variations of this amplitude changes with temperature, which allow us to extract the effective masses using the Lifshitz-Korsavich formulas. And these effective masses that we extract should be affected both by electron-phonon interaction and electron-electronic interactions. And these are the data of probing the changes in the effective masses for the largest pocket we see in quantum oscillation, which is the outer Hall pocket, the delta band. And what it shows us that the effective masses do not have divergent behavior in the vicinity of the nematic endpoint. Instead, all the collated data from specific heat from the A coefficient point out to a behavior which is represented by this color curve, that there is a small enhancement inside the nematic phase, and then the behavior decreases away from it.
And what about the mass enhancement of the other pockets?
It's here. So we can follow the behavior of these two pockets from the data. So we can follow these are the outer electron pocket, which increases, but then we can't see it anymore. And then we can follow the behavior of that very light dominant frequency, which is this lambda pocket, which seems to decrease. Now, this is a summary of all the data on this family of compounds from quantum oscillations. What we have is that Fermi surfaces always expand. So we are going from a strongly correlated system towards a Fermi liquid, and these Fermi surfaces keep getting bigger and bigger. At the same time, the effective masses are decreasing as we expect as we go towards the sulfur end. But the divergent signatures do not occur to the nematic endpoint. If anything, there seems to be a shift, and the enhancement is inside the nematic phase. This correlation can be also tested with ARPES. This is the iron sulfur end here, which has much steeper dispersion compared with iron selenium. And one can estimate the Fermi velocity and see that they increase significantly as we go towards the sulfur end. In here, we've done similar experiments, again with pressure, to probe the behavior to be sure that this is not just a fluke, because we have different type of samples. Here we have a single sample in a pressure cell, and we follow the behavior of the same band of the whole pocket, the delta band, and the blue points are what happens to the effective masses. So they are quite strong, large, about 5 inside the nematic phase, and then they decrease. And you can see that there's no divergent behavior at the nematic endpoint. Unusually, what happens to the effective masses correlates very well with TC in this regime. And whereas as we go to higher pressure with higher TC, this effective masses are actually not growing that much anymore. It seems to be a surprising low effective masses, a high pressure when TC increases a factor 3. So this is something we are trying to work out why is the case. And to summarize here, the trends under pressure, which are also the trends with the chemical pressure, inside the nematic phase, we have heavy masses with, and it's a strongly correlated materials with low Fermi energy. But as we move away from the nematic phase in the tetragonal phases, the Fermi surfaces expand and the masses are slightly changing only outside in the nematic phase. So now why we don't have divergent effective masses at the nematic endpoint, critical point? One reason for this is that the system has a finite coupling with the lattice. So here on the left, it's been shown that structurally the transverse acoustic phonons correspond to the lattice distortion. And this nematoelastic coupling are likely to affect the critical fluctuations. This is a phase diagram built by Paul and Garst, which show that the finite coupling with the lattice are likely to shift the position of the nematic critical point in the first place. Additionally, nematic fluctuations and critical fluctuations are only allowed in certain directions. So if we measure a quantity which is orbitally average, then we are likely to pick this effect. So one reason is for this finite coupling with the lattice. Now resistivity outside the nematic phase seems to have a power law of 3/2, both when we tune with chemical pressure and applied pressure. And this again needs to be understood where it originates. Is it again evidence for the acoustic phonon coupling or some other reasons? And here, another unusual thing we observed when we use pressure was that the magnetoresistivity curves in magnetic field had an unusual crossing. So this is for sample B, very close to the nematic endpoint. This was another sample measured at the same time in the cell, sample C. Again, the crossing is not as good, but very close. And we perform a magnetoresistive scaling of these curves due to the presence of crossing point using this expression, which is usually used in analysis to determine critical exponents. And what we found that the parameters from the scaling, the Z mu parameters, had a very strong activated behavior, which is consistent with the presence of a Griffiths-like phase at the nematic endpoint. In a Griffith-like phase, what happens? You can have very strong fluctuations of the order parameter within the potential nematic islands. Then this will lead to a variation of the critical exponents as a function of temperature and another control parameter, which for us here is strain. It's pressure. And why that will occur under pressure? Well, we have selenium for sulfur substitution. That will cause a small inhomogeneity, but also under pressure, we can also create a slightly different strain, local strain. So those could be the condition to create a rare region into a tetragonal system and create this fluctuation and potentially the existence of Griffiths phases. We observed that this crossing also occurs under strain, which tells us that in iron selenium in this case, between the superconducting to normal transition. So potentially the strain itself is a is a key parameter which could lead to the formation of these phases. And in the last few slides, I'm just going to summarize in a way the role of spin fluctuations in this family of compounds. As I said, NMR have detected that spin fluctuations are likely to exist inside the nematic phase, and they are likely to be responsible for its superconductivity. But the strong coupling with the lattice affects the critical fluctuation at the nematic endpoint. So why superconductivity is not enhanced here as usually we expect if we have strong fluctuation. First of all, indeed, is those fluctuations are suppressed by this nematic strong electron lattice coupling. But also another reason could be that those fluctuations are not responsible for superconductivity. And if spin fluctuations are only found inside the nematic phase, they are dying away as we go outside. In an antiferromagnetic system with quantum criticality, which is barium, iron, arsenide, phosphorus, here one has a spin density wave suppressed and then the superconducting dome. And the quantum oscillations there show a very nice divergent behavior and linear resistivity. So these were the signature we'll be looking for. Well, these are the signatures which occur in the presence of strong critical spin fluctuations. What we found in our system with nematic order is very different from this case. And if we summarize the two systems here, we see that actually TC increases slightly inside the nematic phase. This is where the effective mass also increases. So it's potentially, we have the spin fluctuations, but they are active only inside the nematic phase. And those are the dominant fluctuations which affect superconductivity as compared with the barium 122 system. And lastly, recently we took one of our system, a very, very high pressures. And this time, in this particular system, the nematic and spin density wave are quite separated from each other. And we find a small regime of a fan with a power law which is slightly below 1 in this particular regime. This could be a signature that spin fluctuation and potentially critical spin fluctuation might be operative at high pressure in this particular systems. And this is just theoretical models that tells us about the importance of spin fluctuations in the presence of disorder as well, how we can have different power laws, and also we can create Griffiths phases. This could or could not be applicable for some of the features I presented, but I think they have to be taken seriously into account when we think about the behavior we see in iron, selenium, sulfur. And this is a summary. So I presented the behavior of the nematic electronic phases of a family, actually of two families of iron-chalcogenide superconductors. I show the information we extract from Fermi surfaces and how they change inside the nematic phases, how we detect this unusual dominance of a low frequency which disappears together with the nematic phase and changes in the magnetotransport in the same regime, and the lack of divergent effective masses at the nematic endpoints due to the finite coupling with the lattice, and the potential stabilization of Griffiths phases in that regime. And I think many of the features we observe and unusual Hall coefficient behavior point towards very likely strongly anisotropic spin fluctuations that need to be understood to explain the complex magnetotransport behavior. Well, thank you very much.
Okay, we're open for further questions. Let me start with the question. What's happening to the Fermi surface in the high pressure region where TC goes up a lot?
So,
is it staying the same or is it anything evolving?
So at high pressure, up to the pressure we managed to measure, which is only about 20 kilobar, we see that the Fermi surfaces usually increase in size. So they keep expanding.
Is that both electron and hole pockets?
Yes, yes. They just expand more and more.
Okay. Very good. Other questions?
So this S plus minus pairing symmetry, right, was predicted based on the assumption that it comes from spin fluctuations, right? And looking at the spin fluctuations and the rates of density wave. And so if you now look at these highly anisotropic spin fluctuations, and repeat a similar analysis, with Raphael did something also for the S plus minus pairing and so on. What would you expect here? Is this I think the gap anisotropy was in the tetragonal state, right?
No, that was iron selenium. So the measure, okay, so there are two issues.
So in principle, you have the information about the anisotropy of the spin fluctuations, right? And you also have some information about the gap anisotropy.
So yeah, the gap anisotropy has been measured both by STM and ARPAS data, and they show indeed very strongly anisotropic behavior.
Yes, and does it relate with the anisotropy of the spin fluctuations?
From
assume that there is a spin fluctuation driven mechanism for this.
You mean from a neutron diffraction? So I mean,
you have this gray gradient plot where you looked at the.
So that's the NMR data show that there are spin fluctuations, but they do not tell us how anisotropic they are. I'm not aware. To test the anisotropy in this material, you need to detwin your samples. Otherwise, you measure an average effect.
You said that the scattering has to do with the spin fluctuations, just as an assumption. And then you concluded that the spin fluctuations would be highly anisotropic.
Well, this is the model. Okay, so what we see is that the Hall coefficient becomes very unusual. In a way, it becomes negative in a regime where you only distort the Fermi surface. And your number of carriers in that regime seem to be lost. So in a nematic system where you only distort the Fermi surface, you should not have such a loss, which often occurs if you have a spin density wave transition, or you reconstruct the Fermi surface. So I think it's about how do we understand this unusual Hall behavior, Hall coefficient, in a nematic system. Probably this type of model, strong ellipticity, changes in the ellipticity and of the spin fluctuation due to this are likely to cause an important effect. I think it's about vertex correction, but I can't go into that. I don't know the details of the full calculations.
There's a question here.
Sorry, missed the question. Maybe what exactly is the spin limit?
So it's the development of anisotropy in the spin susceptibility of the system. So when you think why the system becomes nematic, obviously you can think, okay, you have different orbital characters. You can create changes in the occupation of different orbital characters that could give you charge or orbital order effects. But you can also have effects caused by spin sector. So if you have spin fluctuations, those could become anisotropic and drive many of these effects.
The bond singlets can shape S dot S between dependent on direction. Breaking, for example, tetragonal symmetry.
So the dominant
if it was more singlet in the X direction than the Y or something like that, then this would be a spin limit.
Yeah. So it's your susceptibility along A and B direction becomes very anisotropic, or the spectrum of excitation, of course.
I had a question about the anisotropy of the gap that you see. You mentioned that it suggests a strong orbital component or anisotropy. Does it mean that different orbital components have different signs of the gap? Is that what's important for this?
So these are the STM data by Seamus Davis group. And to model the behavior, it's been proposed that obviously the Fermi surface is close to the one determined from ARPA studies. And they had to account for orbital differentiation in the interactions. So they have to assume the XY character will be affected differently from the other orbital character.
But presumably they had to, was it just different sizes or was there a different sign?
They use different Z values, so different, but I don't know about the signs. The title of their paper is The Discovery or Orbitally Dependent Superconductivity in Iron Selenium or something like that.
And the to follow up on Frank's question, the pockets, the electron hole pockets are quite far apart. And normally in a canonical S plus minus theory, you'd want to have strong interactions at the Q vectors that link the positive and negative signs. Is there a sign of spin fluctuations that have the relevant Q vector that could do this?
Well, I think this is the one of the potential evidence for that. And there's been some other neutron diffraction to.
Is that powder data?
It could be lots of hundreds of single crystals, I think.
Is that's Q vector going out along the x-axis, momentum?
So here I haven't checked the exact values,
it's energy.
but it's been suggested that the development of this peak in neutron diffraction seems to be equivalent to the nesting vector between the electron and hole pockets.
Ah, I see. It seems to have the right Q vector.
Yeah, and also the magnetic order which some systems enter into.
Yes.
Collinear antiferromagnetic order seem to have the right Q vector as well.
Okay. Any other questions before we break for the day? Let's thank Amalia.
At 10 o'clock here tomorrow. If we haven't been looking at it. Anyone who wants to go to the pub, I'm sure some of us will be going.
We'll probably go down there for a few minutes or longer.
Yeah, I need to, but I'm on my bike. Well, not all the way to Oxford, just to